Now we understood what are the equipments which are coming in the substation. Now let's go to the, this is the general description for each and every equipment. I will share you this presentation so you can have this. And I request you to please check the definitions of it. Yeah. Yes. Now let's talk about the reliability. Now let's talk about the reliability. Let's see this. For a 200 megawatt of substation, for 200 megawatt of substation, as per the guidelines team, as per the industry and developer practices, each feeder, each 33 kV feeder each 33 kV feeder can carry up to 25 to 30 megawatt of power as per economical choice of transmission line voltage. As per economic choice of transmission voltage. So now let's see, in our case, a 200 megawatt of project, each wind farm, I already told, each wind farm is designed for, is generating 2 megawatt of power in 33 kV voltage, in 33 kV voltage, and the current will be 37 amps. The current will be 37 amps. So 2 megawatt of power, 33 kV voltage, and the current is 37 amps roughly, each turbine. So for 200 megawatt, we need 100 machines. We need 100 machines. So as we done in our earlier class, the economic choice of the voltage using that formula and as per the utility guidelines by checking the losses and the transmission line cost, everything, they decided that the maximum power for that can be pumped through the 33 kV is 30 megawatt of power. The maximum that can be allowed with 33 kV voltage, okay, that is only 30 megawatt of power. 30 megawatt of power. I'm not telling that you are not, you cannot pump 200 megawatt in 33 kV. You can pump team, but we discussed this. When you are going for a high megawatt scale in the low voltage, the current is very, very high, which leads to the losses. And also, which again you required a big conductor to carry that much of current, which again results to the high design of towers. Generally 33 kV, a single pole, which is a 12-meter height. This is the general design of 33 kV voltage transmission line. If you're going for a higher conductors, that conductor weight cannot be bearable by this, withstand by this tower or the pole. So you have to lay a 220 kV towers where you can see in the remote areas. So these towers to be used for 33 kV case. So what you're doing, you are sending the power in 33 kV, but you are putting a cost, but your capital cost is 220 kV. Again, you are losing the losses. You are losing the money in the losses. If you go for 220 kV, the current is very low. Then it's better to go for 220 kV. Why 33 kV? So that is the economical design. So from this, it was concluded that by checking the analysis and everything, 30 megawatt is the maximum power that can be that is a good way to load on the 33 kV system. So in our case, for 200 megawatt, let's assume we allowing 20 megawatt on each line. 20 megawatt on each line. For example, on each line. Each line, one line is can withstand for 20 megawatt of power. So now, how it is? Suppose this is my wind farm. I'm having turbines here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here are some turbines like this. So this is my substation. Now, this 100 machines, each feeder, each line I said, is should be standard for 20 megawatt. 20 megawatt. So for total 200 megawatt, how many lines will come? Nearly 10 lines will come into the substation. 10 lines will enter into the substation. And each line is connected with 10 number of feeders. Like I am drawing a line here. I am doing the line here. This is the 33 kV line, which is traveling like this and coming to my substation. So I will connect this to here, this to here, this to here, this to here, this to here. Yes. So 1, 2, 3, 4, 5, 6, 7, and 8, 9, and 10. And other line is coming like this. This 1, 2, 3, 4, 5, and suppose 6, 7, like that. So these 10 feeders to 10 WTGs are connected to this line. So this line is capable for 20 megawatt. So for 200 megawatt, how many lines are entering into my substation? 10 lines are entering into my substation. Am I clear, team, till now? Hello?
Yes, sir, clear.
Yeah. So 10 lines are entering into my substation. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. These are the lines entering into my substation. Now, for 200 megawatt of power, this is also one case of reliability. Am I right or wrong? If I take, so I said that we can take only 30 megawatt as a load, right? Suppose what I will do is I will check other I will explain this in our next classes. We are having a conductors like HTLS conductor, which is a high tension low sag conductors. In this family, we are having one conductor which is ACCC conductor, which is aluminum carbon composite conductor. Generally, we all aware of this ACSR conductor, aluminum conductor, steel reinforced. This is the conductor coming from the HTLS family. What is the advantage here is, suppose the ACSR conductor, the 400 square mm ACSR conductor will carry 200 amps, suppose. ACCC conductor, which is of same size, same weight, but the current carrying capacity is 400 amps. So now what you can say? Yeah, now what you will say is, then Santosh, I will go with the ACCC conductor. Then I can minimize these number of feeders into only few 1, 2, 3, 4 by taking each 50 megawatt capacity. Am I right, team? This can be possible with the ACCC conductor, but the cost is nearly 3 to 5 times more than the ACSR. Then you said, okay, I am very fine with the cost also. I am having a lot of money for this. Then what you are losing, team? In the 33 kV network, which is traveling some far kilometers to the forest or the remote, 33 kV network, we are not give, because this line is a kilometer. Per kilometer, it will cost only 25 lakhs or 18 lakhs of rupees. 33 kV per kilometer, the line cost is 18 to 20 lakhs. 18 to 20 lakhs. So for this, generally, we won't recommend distance protection, differential protections. Okay. We are not having the unit protections, generally overcurrent at fault protections. So there is no good protection for this line also. Only overcurrent at fault. So the fault level, the fault occurrences is high in distribution systems compared to the high voltage systems. High voltage systems are very stable compared to the distribution one. Am I right or wrong, team? Yes or no? Right? Yes. So what is this? So each feeder now I am having with 50 megawatt. Then if suppose a feeder was lost, then how much megawatt I am losing, team? 50 megawatt of power I am losing. Suppose if I export 50 megawatt of power in a day, I will get 1 crore of rupees to my bank account. 1 crore rupees to my bank account. Now, by this, I am losing 1 crore. Suppose if I split this 50 megawatt into 25, then I will lose how much? Only 50 lakhs. 50 lakhs of rupees I am losing per day, suppose. With a capital investment of 25 lakhs. See, by doing the capital investment of 25 lakhs, I am saving 50 lakhs of rupees per year, suppose. This is the one. This is also reliability. Reliability means checking all these things with respect to the capital and the returns. And in the 50 megawatt, the losses will also be high, 25 low. So by all these conditions, it was decided that 20 megawatt is a good economical one in terms of the losses, in terms of the capital cost, and in terms of the reliability. So we done the reliability up to here, and we decided 10 number of, 1, 2, 3, 4, 5, 33 kV lines, and this 33 kV lines. Total 33 kV lines was entering into my substation. Now again the reliability I'm checking. So how many transformers I required? For 200 megawatt, you can tell that, sir, I will go with each one transformer to each one. Each feeder, I will place one transformer, which is 20 MVA transformer stepping the 33 kV to 220 kV. So one design, one of our members, suppose I designed the subs layout, designed the single line diagram with 10 numbers of 20 MVA transformer. This is my design. Oh, theoretically it is good. Fine. Practically also it is fine. Okay, fine. Now, other person came, he said that, so the capital cost is very, very high. You are creating 10 number of base. Each 33 kV bay team, I am giving the costing also. Each 33 kV bay cost you 25 lakhs. And each 220 kV bay cost you 1 crore. Okay. Forget about the transformer for time being. Okay. So now, if I am placing 10 number of transformers, what would the cost? 2.5 crores in 33 kV and 220 kV 10 crores. So total For this, that project cost is 12.5 crores. Next person he came, no. I will place only one transformer. He is saying, I will place only one transformer. I will connect all these tubers and I will take only one. And he's saying that I will take only one transformer, which is 200 MVA transformer. Okay, he's also right. 1 into 200 MVA transformer will cost you again 25 plus 1. It's like only 1.25 crore. 1.25 crore. Very highly drop in the capital cost. And one more person came. He said, but this is very high reliable. This is very low reliable. I want to do the optimization here with respect to the cost and with respect to the reliability. So he decided to go with two numbers of 100 MVA transformers. So he design is 2 into 100 MVA. And now the cost would be 2.5 crores for him. And other person, he came, he's saying that if in this case, if you are losing the transformer, total megawatt you are losing. Here, if you lose one of the transformer, 100 MB megawatt of power you are losing. Other person came, he said that I will go with 3 into 100 MVA transformers. So if to one of the transformer is failed, still he can pump 200 megawatt of power. Still he can pump 200 megawatt of power. So that is 3 into 100 MVA transformer, which cost him 75 plus 3. So it's like 3.75 crores. So now if you check the cost, the cost here is very high and here is very low. Fine. And come to the reliability. Cost, you have seen that this is the curve. And if you see the reliability, this system is having a high reliable, this system very low reliable. So reliability like this. Up to which extent you require? You require low cost or this. So you have to decide this optimal point where it's satisfying both the cost and the reliability. One person will tell that I have done the analysis and I am finding that the failure of a transformer is twice in a 20 years. One person came, he says that I am not only bothering about the transformer, I am also checking the breaker, CT, lightning resistor, all the things which are connected to this. If any one of the component is failed, whole the system is failed. The reliability. So they have done the reliability, and someone says, why to place 3 number of 100 MVA transformer? 2 into 100 is quite big, fine for my system because my project is a solar project. I can do the maintenance during the night. If any problem was there, at only 12 hours generation, I can attend the maintenance during the night. So I don't want the reliability here. Some will says, my system is a coal-based system. All the input is in my hands. And my tariff is also very high. I have to export the power continuously without fail. So I can gain 10 rupees, $10 per kilowatt hour. If the tariff is very high and the project is continuous, the input, the source is in your hands, the coal, then he will go with 3 into 100 MVA transformer design. So it's totally depends upon the project and the up to what extent the reliability is required for that project. So the reliability analysis will give you that up to what extent you require that reliability. That reliability analysis we will discuss in our next classes, that we were discussing as per the standard of IEEE 493 Gold Book. So I will give you a brief explanation of how to calculate the reliability analysis and how to decide which option is the best one here. So my conclusion here is, by doing all this one, I decided for my project, 2 into 100 MVA transformers is a good enough for my system. 2 into 100 MVA transformers is a good. So these two are connecting to a bus, and all my 33 kV feeders or 10 number of feeders I'm connecting to this. 1, 2, 3, 4, and 5. And these 5 feeders are connecting to this. Fine. And again, these two are connecting to a bus. And again, 2 lines, suppose again the reliability on the lines. Generally, always 2 lines will go out from your substation unless the utility is not allowing you. Mostly 2 lines will be there. If one of the line is failed, other will be there. So this is the skeleton view of your system. This is the skeleton view of your project. Now, the reliability there, 20 megawatt only the loss here. Here, 100 megawatt loss. Here, no loss. If it fail, you can pump this power to this. 2 fail, then whole power is loss. So some reliability are maintaining at every stage. Then what about this node? What is the chances of failure of this bus then? What is the chances of failure of the bus in 220 kV level and in 33 kV level? And is this the configuration is best or any other configurations to be adopted? Again, the concept of reliability. The reliability analysis again will gives you what type of busbar scheme to be adopted in your system. We are having different busbar schemes, team. It's not a standard. You can do as your own. Again, that should be approved by the as per the CE or PGCL or state utilities. Otherwise, you can do the scheme as you want, as you wish. For the reliabilities, again, we are having a different busbar configuration stream. Now let's see. Different busbar schemes. Let's take an example of 4 incomings and 2 outgoing stream. These are the 4 incomings and these are the 2 outgoings. This scheme, 4 incomings are coming and going 2 outgoings. This scheme we will call as a single busbar scheme. Only a busbar. What is the disadvantage in this? If the bus is failed, or if you want to take the bus into the maintenance, total plant should be in shutdown. Total plant is in shutdown. All the power is depending on this bus. But this scheme is very cheap, very easy for to develop the schematics, everything. So, and to make it more reliable, what other scheme was developed is splitting the buses. He person done 2 feeders and he placed a breaker here. Now, what he will do is, generally this will be in open condition. So he will export the power through this and he will export the power through this. Now, if this bus is failed, only 50% of the power is lost. So other 50% is sending through this line. Suppose if this line is failed, then I will close this breaker and all the entire power of 100 megawatt is cooling through this line. So this scheme we will call as a single bus bar with the sectionalizer scheme. Single bus bar with sectionalizer scheme. And to avoid this 50% of the shutdown also, one more scheme was developed, that is double bus bar scheme, where two buses, four incoming lines are connecting to two buses, and these are the two outgoing lines. These are connected with the help of the isolator stream. Now, so generally all the two buses will be in open or will be in the closed position. So the power will be shared on the both and it will go to this. Suppose if one of the bus is failed, then the power, all the power should be shut down, and I will open up the isolators. All these isolators will be opened up because isolators cannot be operated in the load condition. And I will close all the isolators. Now the power will be pulled through this breaker, through this bus. Some interruption of power is there, but good reliable than this. Some interruption of power is there. So to avoid that interruption, four incomings, two outgoings. And to avoid that interruption, we are having a scheme called double bus with the bus coupler scheme. This is the bus coupler. Double bus with the bus coupler scheme. In this scheme, suppose if I want to take this bus into the maintenance, what I will do is generally two buses is in the live position. Okay. Now I can open up this one. I can suppose let's see in this way. I'm having connecting this all the breakers. Okay. Now, if I want to generally now this bus is in the running position. Now I want to shift this bus to this one, and I want to take this into the maintenance. Then what I have to do before, why I have not closed these isolators and opening the isolators? Because this isolators cannot be laid. These isolators cannot be operated in the load condition. Here, with the help of this bus coupler, what we can do is, I will close this bus coupler. So the potential will be transferred to this bus. Now this bus is having 220 kV potential or 33 kV potential. And this incoming node, this is also same potential. If the both potentials are same, you can close the isolator, you can open up the isolator. So without interruption, you can transfer the power from one bus to other bus, and that also two buses, everything can be done with this. This scheme we will call as a double bus with the bus coupler scheme. And now these are the developments on the busbar reliability, And so many schemes are there, like single bus with a transfer bus scheme, double bus with a transfer bus scheme. So let's see the double bus with transfer bus scheme. So in that scheme, they are much more worrying about, see, this is my incomings. These are my outgoings. Now, this scheme, in this busbar scheme, they are worrying about the breakers. The breakers, we are having four breakers, right? For the incoming lines and for the outgoing lines. Suppose if the breaker is failed, the power will fail, right? So what we are doing is, let me make it. This is the bus coupler. And this is the one more sectionizer which is connecting this. which is connecting to this bus. Now, we are taking a bypass. We are bypassing this isolate breaker and we are connecting to here. All the cases we are doing the same. All breakers are bypassing and connecting to this bus. Similarly, here also. Bypassing the isolator, connecting to here. Bypassing the isolator and connecting to here. Now, let's see. Suppose if this breaker is failed, then this power will be transmitted through this transfer bus and this breaker, and it will come to here and it will go to the lines out. It will go through this. Suppose this line is failed, then same, this power will be transmitted through this bus and like this, and it will go to the circuit out. So this scheme is generally designed to maintain for the reliability on the breaker, not on the bus. See, the failure of a bus is very, very low T. See, what is the bus? A conductor, just a rigid bus conductor. What is the failure in that? There is no mechanism in that. Only a conductor. It will fail only due to the poor workmanship or the poor quality of the product. That's it. Or execution, poor execution. So that's the reason in every case you can see only two buses. But the two buses, why so many schemes? Because they are not worrying about the bus there. They are worrying about the breakers. So from here up to the double bus bar, it is fine. From here, the different schemes was adopted, which are with respect to the reliability on the breaker, not on the bus. So the bus bar configurations we are discussing, those not only we are talking about the reliability of the bus, we are also talking about the reliability of the breakers also. And apart from this, we are having one more scheme, which we will call it as a 1.5 breaker scheme. 1.5 breaker scheme, we are having two breakers and two buses and three breakers like this. Three breakers. And we are having two lines, one line, other line, this line, and these are the four incoming lines. And these are the two outgoing lines. Now, let's see. Suppose three breakers are there. If suppose, let me clear you in a big drawing. It will confuse otherwise. It's a very difficult scheme to understand. This is the incoming, outgoing, and this is also one incoming, let's suppose. Now, this power can be transmitted through this breaker. This power can be transmitted through this breaker. This power can be transmitted. It is also incoming, right? Both incomings. This will come here and it will come here and it will go like this. This power will come and it will go like this, depends upon the load requirement. It flows. So suppose if one of the breaker is failed, suppose this middle breaker is failed, then this power will take this route and it will come like this and it will go like this. If this breaker is failed, so for this is the route. So every feeder should be rated for the maximum capacity, not each one. So each feeder should be rated, should be designed for the maximum load, all the load. So that is why it is a very, very expensive scheme, 1.5 breaker scheme. This schemes is generally used in above or equal to 400 kV systems. From 400 kV from 400 kV to above, this scheme is used widely. And for the 33 kV systems, we will use single bus bar or otherwise single bus bar with sectionalizer scheme. And for 220 kV, double bus with the coupler scheme or double bus with transfer bus scheme, like 3 buses for the bypass. So this scheme for 220 kV. And for 132 kV also double bus with coupler scheme. 11 kV single bus bar scheme. And above 400 kV, 1.5 breaker scheme. And above 765 kV, you can see some parts they are using ring main scheme. Like we are having 4 lines, right? This is the one line, this is the other line, this is the other line, this is the one more line. And 2 outgoings. This is the one outgoing, this is the other outgoing. This is all the incomings. So this is the one more line, like they are forming a ring by placing the breakers. They are forming a ring. Now the power, this power will flow. Sorry, this power will flow like this. This power will flow like this. This power will flow like this, and this power will flow like this. Suppose if this breaker is failed, then this power will take all this direction and will reach to here. Suppose if this breaker is failed, these 2 lines will come and will come like this. So this is the ring main scheme. So again, you are forming a ring. So many breakers are required. Again, this total ring should be designed for total megawatt. Total megawatt. Very, very costly scheme. Rarely used. So these are the different bus bar schemes with respect to the reliability. Again, this will comes also on the reliability. Even you've done the reliability and you find that, double bus bar is not suitable for 220 kV for your project. You have to do the double bus bar scheme for 220 kV as per the guidelines. So as per the electrical utility guidelines, it recommending that 33 kV systems, please adopt single bus bar with sectionalizer schemes. And for 220 kV, double bus with coupler or more than that reliable scheme. And 400 kV, obviously a 1.5 breaker scheme. 765 kV, 1.5 breaker or ring main scheme. This is the practice in the utilities. But in some projects, I have seen in the one of the project in Madhya Pradesh, they have done the 220 kV project with single bus bar scheme. That is for solar. What they will say is, during the nights, I will take the bus into the maintenance. I don't want double bus bar scheme. Single bus is very, very fine for me. Because I am not seeing the failure of the bus is very, very low. So they adopted single bus bar scheme for 220 kV also in the Madhya Pradesh. In the Madhya Pradesh, one of the projects we have. So these are all the different bus bar schemes. I am sharing you an article to you. So please read that article so you will get the idea what is the advantages and disadvantages of these buses.